So welcome. This is an historic evening. It was only about 18 months ago that Peter and I had a dinner conversation. Where was that dinner?
We met someplace in Boston, maybe?
And Barry Ptolemy was there. So we actually have footage of that. We have a video record of it.
We were both popping our pills.
And well, I've got mine here somewhere.
Need some water?
There we go. I'll drop one. So, first time I've done that. A year ago, this was a conversation around a conference room table in this building, actually, with Google and NASA. And then a few months later, we had a meeting here at the auditorium with a larger crowd. And it does show the power of human ideas. That's sort of the religion I was schooled in from the age of 3, that human ideas can change the world. And we can do that at a faster and faster pace. Certainly, virtual communication has enabled this project to come together as quickly as it did. And as Peter relayed, we had a fantastic summer program, and it doesn't go without saying, it really wasn't clear to me how well it would come together. I felt it would certainly at least be very promising, and perhaps it had a lot of potential, but there'd be various issues we'd have to deal with. It really is amazing how well it came together. And that is because of the devotion, particularly of the faculty and the trustees and other supporters. And also the amazing students. We had a great admissions process, and we had the luxury of 1,200 applications. And the 40 students who came were remarkably entrepreneurial and creative, and really created the content as much as the faculty. And a number of you were here. In fact, the students from the summer session stand up. Yeah, they're everywhere. There were about a dozen of you at the Singularity Summit we had in New York recently. So we're very excited that all of you have come from around the world, and we do invite your feedback. I'm pretty confident this will be as successful as the summer program, given the care that's gone into it and the experience we had with the summer program. So I'd like to go through my presentation quickly. Let me ask, how many of you have heard me speak before? Yeah, that's what I figured. So I'm going to select some of these slides and talk about some things that are new. I do want to underscore the key point, which is the theme that this whole university is based on, which is exponential growth of information technology. So I may say a few things about that, but I will try to emphasize some new material. The graphs that I'll show you have been updated from the Singularities in your book. And people did ask me, aren't you nervous? Maybe the graphs kind of veered off the curve this time. But I've done this every few years for the last 30 years, and so I was reasonably confident. But it continues to amaze me just how predictable this phenomena is, and that's one of the key points I want to make. But I'll try to go through this quickly, which I think, given the background of this group, I should be able to do, and then leave as much time as possible for some dialogue, get your ideas and questions. We usually end up falling into the rut of talking about consciousness, and that can go on for hours since it's such a slippery subject, and people mean different things by it. Let me start out by underscoring this key point, which is the exponential growth of information technology, which may seem obvious, but it's remarkable how unobvious it is. And one of the reasons for that is that our intuition is not exponential, it's linear. It's the nature of intelligence to make predictions about the future. I mean, that's what intelligence does. We had an inaugural screening of Transcendent Man last night in on the West Coast at the AFI Film Festival in Los Angeles, and that was the first question. Well, what is intelligence anyway? And, intelligence is an ability to make predictions about the future. And when we walked through the savannah 1,000 years ago and we saw something coming at us, we made a linear prediction where that animal would be and what to do about it. And that worked quite well, and that became hardwired in our brains. And so our intuition, our hardwired predictors are linear. And I have this debate all the time with sophisticated scientists who are quite expert in their fields, and they say, well, Kurzweil underestimates the complexity of fill in the blank, the human brain, or the ability to create human level computing or nanotechnology. And I've been involved with technology development for 50 years. I don't think I'm underestimating the complexity. I think I agree with my critics on the challenge of these projects. I think they're underestimating the amount of the power of the tools we'll have to solve these problems because of the exponential growth. And people just think intuitively in a linear manner that the current pace of progress will continue. I had this debate not too long ago with a neuroscientist who was studying one ion channel in a dendrite, and he felt, and this intuition probably was accurate, 1% of that problem over the last year. This will take a century, as if nothing will happen in the next century, despite the fact we're doubling the spatial resolution of brain scanning every year. We're doubling the amount of data we're getting on the brain every year. We're doubling the precision of the simulations of brain regions every year. But none of that's going to affect the pace of his progress. And the Genome Project is a very good example of that, because there were many articles halfway through the project calling it a failure because only 1% of the genome had been finished, despite the fact that 50% of the duration had gone by. But that's actually right on schedule, because you start out doubling little numbers, and it doesn't look like much is happening early in an exponential progression. But 1% is only 7 doublings away from 100%. It literally continued to double every year, very precisely, by the way, as you'll see on my logarithmic graph, for the next 7 years, was done a year ahead of schedule. Same thing happened with the internet. I made a prediction in the early 80s when I was writing Age of Intelligent Machines that there would be this World Wide Web. I didn't call it that, but I described it quite well, emerging in the mid to late 1990s, tying together hundreds of millions of people to each other and to vast knowledge resources, and that seemed ridiculous when the entire defense budget could only tie together a few thousand people. But that's the power of exponential growth, and it's not just Moore's Law. People very often equate Moore's Law with this exponential growth of technology. Spectrum magazine had an issue devoted to the singularity, and there were both supportive and critical articles, and the editors, so every other page put a little profile of people that were significant in the singularity and how long they thought Moore's Law would continue. The implicit message being that this exponential growth is Moore's Law, and it had me down for 15 years, which I think is accurate when it comes to Moore's Law, but that has nothing to do with the exponential growth of information technology. That is the most famous paradigm that is exponential, and that's the one that people are most familiar with. But the exponential growth of computing started decades before Gordon Moore was even born. And it was the fifth, not the first paradigm to bring exponential growth to computing. And it will continue when Moore's Law does end. And a strong proponent of that view now is Justin Ratner, the CTO of Intel, who will tell you that they have the sixth paradigm, which is three-dimensional computing, working in prototype form, and they expect the turnover from flat to three-dimensional circuits to occur in the teen years, well before we run out of steam with three-dimensional circuits. And the way I got into this is because I began to realize 30 years ago that timing was critical to being successful in technology, and that most inventors fail because their timing is wrong. Larry Page and Sergey Brin had a great idea for search engines, but they did it at exactly the right time. And so timing is really very critical. And in these various progressions, social networks like Facebook and so on, you can identify many companies, before and after the one that really takes on the imprimatur of that concept, timing is very important. Have the right idea at the right time. So I began to study technology trends, and being an engineer, I gathered a lot of data, and I really did not expect there to be an easily predictable pattern. I thought maybe if you'd step back and kind of squint at the data, you'd see some kind of trend, but what you're measuring is innovation, creativity, competition, failures, competing marketing programs. You expect that to be the least predictable phenomena possible. And it really is amazing as just how predictable these trajectories are. Now, that doesn't mean everything about the future is predictable. What we do with these technologies is not predictable. There is intertwined promise and peril, and we'll probably touch on that during the dialogue part of this evening's session. And so when we go away from these underlying measures of information technology, we're on a little bit less secure ground, but the power of these technologies is amazingly predictable. And having observed that, I've examined why that's the case, and I've written a theory as to, which I call the law of accelerating returns, as to why that should be the case. Basically, we create more powerful technologies to create the next stage, and you can quantify that, and I have a whole mathematical treatment of that. But none of that would be important at all if the empirical case weren't as strong as it is. And this phenomena goes back over a century. It goes back over a century in computing. I sat next to Martin Cooper last week in London, this session held by The Economist, and he has Cooper's law having to do with the total amount of bandwidth available to transmit information, which goes back to Morse code, and it's over 100 years of very smooth, it's an absolute straight line for the last century, and he's identified the technologies that could continue that for the next 60 years. So if you can measure the underlying properties, and I could list 100 different things like that, the number of bits we're moving around on the internet, the number of bits of data we're getting on the brain, the spatial resolution of brain scanning, different measures of biological technologies, different measures of communication technologies. They follow exponential, not linear progressions that are predictable and exponential, not linear. And although I'm sure you're familiar with it, it's worth underscoring that there's a profound difference, because 30 steps linearly gets you to 30, and 30 steps exponentially, 2, 4, 8, 16 gets you to 1 billion. And that's not just a theory about the future. When I was at MIT, we all shared a computer. It cost tens of millions of dollars. For the technically minded among you, it was an IBM 7094 with 32K of memory. 36-bit words, so it's 150,000 bytes, core storage. Took 2 cycles per instruction, 2 microseconds per cycle, so it's a quarter of a MIP. This computer I carry around is 1 million times cheaper and 1,000 times more powerful. That's a billion-fold increase in the amount of computation, the number of bits per dollar in constant dollars since I was a student, and we'll do it again in 25 years. And we're shrinking technology at a rate of 103 volume per decade, so that's 100,000 in the next 25 years. That gives you some idea of what will happen. And ultimately, these profound quantitative changes create qualitative changes. And then people are amazed at what the future will bring, but when it happens, it's just part of everyday reality. And people forget very quickly what life was like. I mean, imagine life without social networks, wikis, blogs. That was only 3 years ago. Imagine life without search engines. That was only 10 years ago. So the pace of change is accelerating. It does create qualitative changes, and when they happen, we get used to them very, very quickly. So I'm going to only focus on some of these slides, but just to give you an idea of how pervasive this is, I'll try to emphasize some recent findings. The world is already quite different from when Singularity's Near came out, which was already 4 years ago, which is a lifetime ago now with the pace of change. And But then I look forward to sharing ideas and getting some questions that we can all attack. Well, this was my first reading machine in the 70s. It was about the size of a washing machine. It now fits in a cell phone. It's 5,000 times smaller and very inexpensive and does a lot more than the original reading machine. And it's not because we're so clever. I mean, you can buy an iPhone today that's twice as good for half the price. That's a quadrupling of price performance, and it's not because Apple is so clever. We all can take advantage of this profound law of accelerating returns, which is a 50% deflation rate in every form of information technology, not just computation, not just electronics. If you want to buy genomic data, proteomic data, brain data, different kinds of databases, every kind of computational resource, it has a 50% deflation rate, and ultimately it will be everything. Ralph will see to that. We'll be able to print everything out with three-dimensional printers at the molecular scale, and physical objects will also be information and subject to this law of accelerating returns. And a very common question is, well, these new technologies are great, but only the wealthy are going to be able to afford them. And I say, yeah, like cell phones, of which there are now 4 billion in the world. And they're not just cell phones. They do a few other things. According to Apple, they do 80,000 things. I mean, I got back from China recently. Half the farmers in China have these devices. They can access all of human knowledge with a few keystrokes. They can create human knowledge. There's 100 million blogs in China. And really, the common man and woman, so-called, is empowered now to create knowledge that can change the world. And it is really democratizing. I mean, it used to be you had to be a big organization of some kind to create disruptive change. You had to be a Hollywood studio to create a movie. And now a kid in her dorm room can create a movie with her PC and the high-definition cameras are down to 189. It's really impressive. And they're, you can view them in a large theater and they look fantastic. Larry and Sergey, on their $1,000 laptops, did a little dorm math project. It was a dorm room challenge, and that company's now worth $150 billion. And a couple of kids at Harvard wanted to put these photograph books, they were called Facebooks. They were originally, if you remember, paper books where you could see who you wanted to date. And that was the primary function of them. And they wanted to put these online so you could see who you wanted to date online, and then you could actually put some other information other than the photographs. And that was only 5 years ago. They're now 270 million users. So the pace of change is accelerating. I have this whole theory as to why this is the case. And we see it in every evolutionary process. We can see it when we simulate evolution, and we've done a lot of that in our pattern recognition work because it is a powerful technique. Evolution can be creative, come up with these very interesting solutions. Maybe some of you have seen this very interesting exotic three-dimensional design of an ideal radio antenna that was designed with a genetic algorithm. And we do see this acceleration as when the genetic algorithm actually settles on one paradigm and stabilizes some regions of the simulated genome. The next part of the simulated genome that gets settled will happen more quickly. And that's because an evolutionary process, including biological evolution, evolves a capability, like DNA, and then adopts it. And biological evolution used DNA ever since. So the next stage goes more quickly. This is a double logarithmic graph on the x-axis in powers of 10, how long ago this paradigm shift took place, and on the y-axis, how long it took for the paradigm shift to occur. Life, basically DNA, a little computer system that evolution devised to keep track of its experiments, took 1 billion years. But then it adopted it, and the Cambrian explosion happened 100 times faster, and so on. And then we moved to technological evolution, and we always use the latest tools to create the next. And one criticism of this is that I only put the paradigms that fit on the straight line on the graph. So I took 15 different lists, and there is some spreading of the points, but there's a very clear trend line, no matter whose list you use of the key events in biological and technological evolution. And another criticism is, well, Kurzweil just takes these exponentials and projects them out, and we all know exponential growth can't go on forever. 2 rabbits in Australia become 4, become 8, 16, but that doesn't go on forever when they eat up all the foliage. And basically they run out of resources, and we do see that in these paradigms in information technology as well. But what happens is it creates research pressure to create the next paradigm. And so the ongoing exponential is a series of S-curves of different paradigms. That's already happened 5 times in the history of computation. And there are really vast resources available in information technology to continue this process. I have an analysis in chapter 3 of the singularities near what the ultimate limits of computation are, so-called computronium, when we apply Rob and Ralph's technologies to computation, even without getting into exotic things like femtocomputing, but just based on what we really can touch and feel in terms of molecular computing already, and it can keep this graph going in computation for a very long time. So this is updated from the graph in Singularity is Near. That goes through 2002, since that book came out in 2005. This goes through 2008, and it's very much on the curve. And this kind of squashes the progress because each level is 10,000 times greater than the level below it. So this is trillions-fold increase in the amount of computation you get per dollar, a billion-fold just since I was an undergraduate. And so the scale is pretty remarkable. It's also a double exponential because that's not a straight line. A straight line on a logarithmic graph is exponential growth. We have slow exponential growth in the rate of exponential growth, and there's a whole theoretical reason for that. As a technology becomes more cost-effective, we put more resources into it. I mean, in 1950, the computer industry, such as it was measured in millions of dollars. It was a handful of famous projects. And today it's a multi-trillion-dollar industry. So that accelerates the pace of progress. It took 3 years to double the price performance of computing in 1900, 2 years in 1950, it's 12 months in the year 2000, it's now down to 11 months. But I think the most impressive thing about this is just how predictable a progression that is. And I've been making forward-looking predictions for 30 years based on this progression and others. So it's not just back overfitting to past data at this point. But it is really amazing when this is really a measure of the innovation and invention and entrepreneurship of millions of people, and it's remarkably predictable. I mean, it really is worth repeating. And it's an important message in terms of planning projects. Certainly if you're an inventor yourself or an entrepreneur or invest in entrepreneurship, but really for any kind of project. If you're a librarian planning, how to automate the information retrieval, the world's going to be different in 3 years, and you can predict at least the underlying power of these technologies. And this continues through boom times and recessions. The Great Depression had no impact. The current economic downturn has no impact. It's continuing unabated through this current downturn as it has every other downturn, and that's an important point to recognize. And, say in the 1950s, there were shrinking vacuum tubes. That was the way they kept this exponential growth going. There was no such thing as Moore's Law. There were no chips. That hit a wall. Got to a point where they couldn't do that anymore and keep the vacuum. And that was the end of the shrinking of vacuum tubes. But it just went to the fourth paradigm, transistors, and so on. So here again, this is updated to 2008. You could buy one transistor for $1 in 1968. You could buy 1 billion today. That's an impressive amount of progress, but look at how predictable this is. It's really pretty amazing. We're going to be adding Cooper's Law, which is a similar slightly curved line, but it's very smooth, going back to 1890 something on total amount of bandwidth expressed digitally in terms of the amount of information you could move on the world's wireless networks. Transistor cycle is a good measure of price performance electronics. Comes down by half every year. So that's about a 50% deflation rate, depending on what you're measuring, but it's very close to 50% no matter what you look at. And so economists do worry about deflation. There's been some deflation in this current economic downturn, but that's not because of this phenomenon. That's because of a shrinking of demand. We had massive deflation in the Great Depression. And the concern with regard to information technology is more and more the economy becomes information technology. And we just added another industry, health and medicine, which didn't used to be in information technology and now is. So I'll talk in a few moments about how energy is becoming an information technology. And if that has a 50% deflation rate, it's going to shrink the economy because people aren't going to double their consumption year after year of every form of information technology. They'll increase somewhat, but they're not going to double their consumption. That's the concern. But actually, that's not what we see. We more than double our consumption. We've had 18% growth in every form of information technology in constant currency over the last 50 years, despite the fact you can get twice as much of it every year for the same cost. And the reason for that is as price performance reaches certain levels, whole new applications explode on the landscape. So people didn't buy iPods for $10,000, which is what it would have cost 15 years ago. And NIH wouldn't be collecting 1 million genomes if they still cost $1 billion each, but at $1,000 each, they're willing to do it. And this is bits shipped, but you can measure. We see the same phenomena in the application of every other form of information technology. This is, in fact, what's driving economic growth, because more and more industries are becoming deeply influenced, if not entirely comprised of information technology, and that portion of the economy, which is growing as a percentage of the economy, has an 18% growth rate. The non-information bearing technologies have a negative growth rate. Magnetic data storage, this has been updated, and I just put this up because this is not Moore's Law. These are different engineers. It's a different engineering problem. We see the same progression. And biotechnology, that's a very important example because everybody cares about it. It affects something that's even philosophically important, our longevity. And it didn't used to be an information technology. It was a hit or miss process. And as such, it was not progressing exponentially. It was progressing linearly. And we see progress in non-information technologies, but it's not exponential. It's still been pretty useful. Human longevity was 23 1,000 years ago, 37 in 1800. But now it's an information technology. We have the software that life is based on. It is a software process. We have 23,000 little software programs running in our body. They evolved thousands or even millions of years ago when conditions are very different. And each of those genes is a software program. It's not written in C++. I think it's written in COBOL. But they express themselves as three-dimensional proteins. I had a debate about 3 years ago with the biologist saying, well, there's certain mysterious things about biology we will never understand or simulate with digital computers, and one of those is protein folding, this magical thing where you have a linear sequence of DNA, gets copied to RNA, and then the ribosome creates a linear sequence of amino acids, and then the magic happens. This linear string of amino acids gets folded up into a three-dimensional protein, and that is magical. He didn't use that word, but we'll never understand that. I said, no, I think when we get to 10 to the 13th calculations per second, we'll be able to simulate that. And indeed, in this past year, about a year ago, we can now simulate that for certain length amino acid strings, and now every month they're adding longer and longer strings. And we can actually take an RNA sequence, a gene, and predict the protein that it will create. And we've had very smooth progression in the cost, gone from $10 per base pair to a small fraction of a penny today. We've doubled the amount of genetic data very smoothly. It's remarkable how smooth these curves are. And other aspects of biology are scaling up at a similar exponential manner. The proteome project and other aspects of reverse engineering this object code. In 2003, we had the object code. We didn't really understand what it meant, and we're still in an early stage of doing that, but we are reverse engineering biology, and that's scaling up at an exponential pace. And communication technology, there's 50 different ways to measure this. This is that graph of the internet I had. Well, I had a few points of it, kind of like what Gordon Moore had with the first few chips. Moore's law came literally from a napkin where he had 3 points of chips and then projected that out, and that has held up now for quite a few decades. It's certainly an important example. This same data looks like this on a linear scale. So to the casual observer, it looked like the World Wide Web came out of nowhere, but you could see it coming. We're shrinking technology at an exponential pace, and these early illustrations from Eric Drexler's Engines of Creation, which is now over 20 years old, we are starting to build. So this is Rob Freitas's conception of a robotic red blood cell. There are actually early examples of experiments in animals with blood cell-sized devices, like the little device with 7 nanometer pores that can cure type 1 diabetes in rats, and other examples. And this particular example from Rob Freitas of a robotic red blood cell, which is something we do understand, red blood cells that is a good example of the ultimate benefits of nanotechnology as applied to biology, which is, biology is very clever, it's very intricate, but it is suboptimal because our evolutionary process made certain assumptions and had to build on those, and so it made compromises along the way, like building everything out of proteins, which is a limited class of materials. And we won't have these limitations. It did have a way, though, of circumventing those limitations, which it evolved a creature that was intelligent enough to imagine changing these early assumptions, and we have an opposable appendage. And even though this is kind of clumsy to actually go in there and change molecules, we do have this ability to do hierarchical thinking and to leverage our abilities so we can create tools that allowed us to manipulate things even more finely than we can with our hands. And ultimately, we will have hands that can manipulate molecules. We can already do that experimentally. And we won't have the sticky fingers problem because Ralph and Rob have pioneered means of actually manipulating molecular fragments, and we can see our way to a molecular assembler. But the key point is that we can go beyond the limitations of biology. And that's in fact what human beings are all about, is if we didn't go beyond the limitations of biology, none of us would be here, because as I say, life expectancy was in the 20s 1,000 years ago, which is not so long ago. So we'll have plenty of computation as we go through the 21st century, and that is not so controversial. The more controversial aspect is really, will we have the software? And my view of reverse engineering, sometimes people say, well, Kurzweil's plan is to reverse engineer the human brain and simulate it, and that's how we'll create the software of AI. My view of the purpose of reverse engineering the brain is twofold. One is it's an existence proof that we will have the software of intelligence because we are making exponential gains in understanding the human brain. But also the purpose of it is not just to mechanically simulate a brain without understanding what's going on, and that's how we'll create AI, human-level AI. The point is to actually understand the principles by which the human brain produces intelligent decision-making. And then engineering can come along with those principles and amplify it and focus on it, and it won't be limited to a substrate that's 1,000,000 times slower than electronics. Transmitting information as electrochemical signals that travel a few hundred feet per second. It won't have to fit into a 1 square foot skull. The big innovation in human beings is that we have a bigger forehead, so we could fit a larger cerebral cortex. Consider what engineering did with Bernoulli's principle. It's a subtle scientific principle. It says there's slightly less air pressure over a moving curved surface than a flat moving surface. And the scientists still argue about why Bernoulli's principle is true. It's derived from thermodynamics, and there's still arguments about that. But engineering technology came in and focused on it and amplified its powers and created the whole world of aviation. And that's what we'll do with the basic principles of intelligence, some of which are becoming clear. And there's already models and simulations of different regions of the brain. This is all scaling up exponentially. The auditory cortex, the visual cortex, the cerebellum. This is a picture from the cerebral cortex, which has been, at least slices of which have been simulated with the Blue Brain project. The head of that project, I was on a panel with him recently in Israel, and I was actually refreshingly the conservative on that panel, because he was saying we'll finish reverse engineering the brain by 2018, and my view is it's 2029. But one of my critics, John Horgan, cited this picture saying, well, look at the complexity of the cerebral cortex. This is just a portion of it. This is incredibly complex. We'll never understand this. At least it's going to take centuries. So I researched this picture because I was due to have a debate with him on stage, and discovered this is not a picture of the cerebral cortex at all. This is a picture of a simulation of the cerebral cortex. So by definition, we have, in fact, figured it out. Well, this graph is worth pointing out, which is this is e-commerce. People say, well, where's the boom bust that we had in dot-coms? And that was a Wall Street phenomenon, not a Main Street phenomenon. And in fact, this boom-bust psychology is an accurate harbinger of what ultimately is a profound revolution. So people see this revolution coming, and then the valuations go haywire, but they don't have an accurate model of when these things will happen. Because you start out, exponential growth is not instantaneous growth. You start out doubling little numbers. So Wall Street came back in the year 2000 and said, gee, it hasn't changed everything. It hasn't changed anything. I guess we were wrong, and all the values went the other way. But meanwhile, it was chugging along exponentially, and you have dot-coms today like Google with $20 billion of revenue. And we saw the same thing even in the railroads in the 19th century. So I'll show this graph. I recently met with the Prime Minister of Israel and talked about this because he had been talking to other people about solar energy, which Israel does lead in, but they were looking myopically at today's limitations and thinking about, well, using these current technologies, what we can do, and it's not really quite cost effective. Transform the world with solar, and it's only 0.5% of the world's energy needs, and maybe we'll make a little progress. We're applying nanotechnology in an early stage to solar panels. Solar panels have been coming down rapidly for 20 years, and this is a graph on a logarithmic scale of the total amount of solar energy in the world. It's doubling every 2 years, and it has been for 20 years. There's been 10 doublings. But people tend to dismiss a technology, even if it's exponential, when it's only 0.5% of a solution. They did that with the internet, they did that with the genome, and they're doing that with solar energy. It's only 8 doublings away from meeting 100% of the world's energy needs. And Larry Page and I did a thorough study of this for the National Academy of Engineering and concluded that solar had the most headroom because there's 10,000 times more sunlight than we need to do this. So the next day, then, Netanyahu announced at the Israeli Presidential Conference a major Israeli initiative to have a 10-year program to replace fossil fuels with solar energy and other renewables like wind, with Israeli technology and enterprises taking the lead, kind of like Kennedy's 10-year plan to put a man on the moon. And this is going to happen. And people say, well, if we radical life extension, we're going to have more population, we're going to run out of energy, all these Malthusian concerns. We're awash in resources. There's 10,000 times more sunlight than we need to meet all of our energy needs. But we haven't been able to convert it. But these new technologies are going to convert it into a usable form. The same thing is true of water and food, and if we had more time we could talk about those. Even housing, we had a very enterprising project in that sphere at the summer program. So I'll just leave you with this. This is from the linear progression of health and medicine. It's certainly been useful. And now health and medicine is an information technology. It's going to progress exponentially. And we're getting to an exciting part of it. That there's 1,000 projects already underway in the development and testing pipeline to change our genetic code using things like RNA interference to turn genes off in a mature individual, new forms of gene therapy to add new genes, and otherwise reprogram the information processes underlying biology. So thank you very much.